Hey everyone, in this video we're going to learn about recursively defined sequences. To start, they've given us a sequence consisting of the numbers 3, 7, 11, 15, and continuing on. So first, notice that a sequence is a list. It's an ordered list of objects. In this case, it's a list of numbers, 3, 7, 11, 15. Each number shown represents a term of the sequence, so 3 is the first term, 7 is the second term, 11 is the third term. That answers the first question. Which number is the third term of this sequence? That would be 11. And then 15 would be the fourth term. If we wanted to list more numbers out in this sequence, we need to identify a pattern. So what pattern do you notice in the terms of this sequence? Look at the terms they've given us, 3, 7, 11, 15. We should notice that the pattern is to add 4 each time. So 3 plus 4 is 7. 7 plus 4 is 11. 11 plus 4 is 15. It's important to make sure that the pattern that you recognize works for all of the terms that they've given us. So 3 plus 4, 7 plus 4, 11 plus 4. Because we might notice a pattern between the first two terms that doesn't hold up as we continue on. So we want to make sure that pattern works for all the terms we've been given. So let's write that down. What pattern? Our pattern is to add 4 to get from one term to the next. So what is the number that would come after 15 in the sequence? Well, we're going to continue the pattern of adding 4, so the next term would be 19. So the fifth term of this sequence is 19. Now is an important time to stop and point out that not every sequence has to have a pattern. If I had everyone make a list of 5 numbers, most likely your list would not have a pattern in it, unless you intended it to. In this course, we're focused mainly on sequences that have a pattern that we're trying to recognize. So it's just important to make note of. There's an infinite number of sequences. We're focused on the ones that have a pattern that we can recognize. So to formally define a sequence is an ordered set of mathematical objects. Put more plainly, it's an ordered list of things. In the first example, it was an ordered list of numbers. Could be a list of shapes, could be a list of symbols. Any of those would be categorized as a sequence. Now when we're working with sequences, we have a new notation. So to help us describe different terms of a sequence, we use a special notation called subscript notation. And that's right here, A sub n. So we pronounce it A sub n. And that's just to indicate that n is the subscript in the notation, and it represents the value of the nth term. So the first term would be A sub 1, second term would be A sub 2. This works similar to function notation. Right? If we had f of x, that's our function notation. X is the input, f of x is the output. So in subscript notation, n is the input. What term of the sequence are we dealing with? A sub n is the output. It gives us what the number is. So if I take the previous sequence, 3, 7, 11, 15, you can see subscript notation here. So A sub 1 was equal to 3. So what does that mean? The first term of the sequence is 3. A sub 2 equals 7. The second term is 7. A sub 3 equals 11, and A sub 4 equals 15. So essentially we're inputting the n value, the term of the sequence, 1, 2, 3, or 4, and our output is what the number in the sequence is. So now that we have that established, we notice the pattern was to add 4 in this sequence. Can we represent that mathematically with subscript notation? The answer is yes, but we need to work a little more with subscript notation before we can do that. So in a sequence, which term comes directly before the fifth term? So that would be the fourth term. And after the fifth term, that would be the sixth term. Now, what if I wanted to generalize this idea? What term comes directly before the nth term? Well, before n would be n minus 1. So we have the n minus 1 term. And after n Well, that would be n plus 1. So we've dealt with this idea before. Go back, remember consecutive integers? When we defined our let statement, we let x equal the first integer, x plus 1 be the next integer, x plus 2 be the integer after that. We're doing the same thing here. 4, 5, 6, right? That's counting 4, 5, 6. More generally, we could have n minus 1, and then n plus 1. So what if I wanted to write out a sequence in just subscript notation? Like below. We have a sub 1, followed by a sub 2, followed by a sub 3, followed by a sub 4. So what comes next in that sequence? Well, that would be a sub 5, right? The first term, the second term, third term, fourth term, fifth term. And now we skip over a bunch of terms, and then we just have a sub n, the nth term. Well, what comes before that? Well, that would be a sub n minus 1, right? N minus 1 comes before n, so a sub n minus 1 comes before a sub n. And then if we were to continue on, next would be a sub n plus 1, and after that, a sub n plus 2. So if you look at the subscripts, it's essentially like we're counting. 1, 2, 3, 4, 5. Skip over a bunch of terms, n minus 1, n plus 1, n plus 2. We're just adding 1 to each subscript to keep going. And then a sub 1, a sub 2, that's our new subscript notation. So now that we've established this idea, the relationship between a sub n minus 1, a sub n plus 1, we're getting closer to being able to define that pattern mathematically. So the pattern for the sequence 3, 7, 11, 15 is we took the nth term, and that was equal to the previous term plus 4. So this is a very simple way to write it. So now the question is, can we represent this in subscript notation? Well, the nth term in subscript notation would be a sub n. The previous term, the term before that, would be a sub n minus 1. Right? If we have a sub n, the nth term, take 1 away from the subscript, n minus 1. So a sub n minus 1 is the previous term plus 4. So this describes the pattern to us. If I want the next term in the sequence, I take the term before it, that's the relationship here, and I add 4. But what other piece of information would we need to be able to create the sequence 3, 7, 11, 15 on our own? Right? Plus 4 is really helpful, but I also need to know where to start. Right? I need a starting value. Well, that is 3, and if we represent it in subscript notation, that would be a sub 1 equals 3. Right? The first term of the sequence is equal to 3. If we combine these two ideas, we get a recursive definition for the sequence. So a sub 1 equals 3, a sub n equals a sub n minus 1 plus 4 is the recursive definition of the sequence 3, 7, 11, 15. So we need two pieces of information to create a recursive formula. We need the first term, and we need to identify the pattern with our subscript notation. So to formalize that idea, a recursive formula defines the nth term, a sub n, as a function of its previous term, a sub n minus 1. It must also define the initial term. Okay, so we got two things to define when creating a recursive formula. So write a recursive formula for the following sequences. The first sequence, 5, -1, -7, -13, -19. First thing we want to do is identify the pattern. So looking at the terms here, I notice to get from 5 to -1, we can subtract 6. But I need to make sure that always works. So -1 to -7, that would be subtract 6. -7 to -13, subtract 6. -13 to -19, subtract 6. Okay, so our pattern is consistent. We're subtracting 6 to go from one term to the next. So the recursive formula, first thing, need that starting value, the initial term. So a sub 1 is equal to 5. Now we need to define a sub n in terms of the term before it. So a sub n is equal to a sub n minus 1, the term before it, minus 6. Really important that we are neat when we're writing this, because we want to make sure that n minus 1 is in the subscript, and it doesn't look like we should be doing minus 1, minus 6 in our work. You may want to put a set of parentheses around that n minus 1 for those of you who have not the neatest handwriting. Okay, so there's the two pieces of information that create our recursive formula. So here's what a recursive formula is really good for. It's good for knowing where the sequence starts and what the pattern is. Subtract 6. What it's not that great at is finding like the 100th term of the sequence. Because to find the 100th term, I need the term before it, right? That's what this is saying. Find the 100th term, I need the 99th term, 100 minus 1. Well, to find the 99th term, I need the 98th term. And we can see how that is going to continue all the way back till we get to the 5th term. So we'd have to list out the 5th, the 6th, the 7th, all the way up to 100. Not very practical to do that. But it is really good at saying, this is where it starts, this is what our pattern is. So let's look at our next example. 2, 6, 18, 54, 162. So it definitely doesn't look like we're adding by the same amount each time. Maybe multiplication. So 2 to 6, that would be times 3. 6 to 18, that would be times 3. 18 to 54 times 3. 54 to 162 is also times 3. So our pattern is consistent through all of the terms of the sequence. So our recursive formula, a sub 1 equals 2. We're starting the sequence at 2. And a sub n is equal to the term before it, a sub n minus 1, times 2. Nope, not times 2, times 3. Times 3. And if we want, we can clean that up and write that as a sub n equals 3 times a sub n minus 1. Right, so we've seen a recursive formula where we're subtracting or adding, and a recursive formula where we're multiplying to get from one term to the next. Now, Janice wrote her recursive formula for the sequence 5, negative 1, negative 7, negative 13 as a sub 1 equals 5 and a sub n plus 1 equals a sub n minus 6. Now, that's almost identical to what we had, except she used a sub n plus 1 and a sub n. So is that okay? The answer is yes. She is correct. Now, why is she correct? Well, the idea of this second equation when we're creating a recursive formula is to identify the pattern between a term and the term before it. Well, a sub n is the term before a sub n plus 1. So we still have that relationship the way that Janice defined her equation. So a sub n is the term before a sub n plus 1. Now, we could get crazy here. We could write a sub n plus 100 equals a sub n plus 99 minus 6. That would accomplish the same thing. That would be a little impractical though. We're going to stick to either using a sub n or a sub n plus 1 on the left side of this equation, and then defining it appropriately based on what we chose. So in the first two examples, we chose a sub n as the left side of the equation. So this term was a sub n minus 1. Now let's do 2 like Janice did. So determine the next term in each of the following sequences, then write a recursive formula for the sequence, assuming n is greater than or equal to 1. The reason determining the next term is helpful, it helps us identify the pattern. So if we're looking here, it seems that the pattern is to subtract 1 to get from one term to the next. So the next term in the sequence would be 11. Okay, so our recursive formula, a sub 1 is 16, and a sub n plus 1, using Janice's notation, is equal to a sub n minus 1. So that minus 1 is not in the subscript. Really important for those of you who have some messy handwriting to be as neat as possible here. Our next sequence, 10, negative 20, 40, negative 80, 160. So the pattern there that I see is to multiply by negative 2 each time. And it seems to check out. So that means the next term here would be negative 320. So our recursive formula, a sub 1, the first term is 10. And a sub n plus 1 is equal to negative 2 times a sub n. Right, a sub n plus 1, and the term before that is a sub n, and we're multiplying it by negative 2. Okay, so the notation is definitely something that we're going to get used to as we do more examples. Now, so far, we've just come up with the recursive formula based on a given sequence. Now we're going to reverse it. We're going to be given the recursive formula, and we have to write out the sequence. Write out the first 5 terms in each recursively defined sequence. Assume you are given the initial term of the sequence. Okay, so our first recursive formula, a sub 1 equals 9, a sub n equals negative 2 times a sub n minus 1. Now I'm going to show as much work as possible here. We're not going to do that every time, but just to really explain this out. First, we want 5 terms, so I'm going to create 5 blank spaces. 3, 4, 5. Underneath each blank space, I'm going to write the term number, so the n value. So n equals 1 for the first term, 2 for the second, 3 for the third, 4 for the fourth, 5 for the fifth. Right? So underneath each blank space is the term number, 1, 2, 3, 4, 5. We know the first term is 9. So now we need to use the second equation to figure out what the other terms of the sequence are. Okay, so if I wanted to do this mathematically, I'd start by plugging n equals 2 in, right? This is n equals 2. So I'd have a sub 2 equals negative 2 times a sub n minus 1, which in this case is 2 minus 1, which is 1. So that's negative 2 times 9, which is negative 18. And then we'd take n equals 3, so a sub 3 equals negative 2 times a sub 3 minus 1, which is 2. What's a sub 2? That's negative 18. So we have negative 2 times negative 18. That's 36. And we could keep writing this out every time. Or we could realize that we're just taking the previous term and multiplying it by negative 2. So next we'd have negative 72, and the fifth term would be 144. Okay, one way to recognize that pattern is to put a box around that previous term, a sub n minus 1. So essentially we're putting 9 into this, a sub n minus 1, multiplied by negative 2, get negative 18. Then negative 18 goes in, multiplied by negative 2, 36. And we continue that pattern forward. So in this case, I'll try to do it with less work. Okay, so we still want 5 terms. 1, 2, 3, 4, 5. I won't write the n values underneath though. So we're starting with the first term of 4. Now this recursive definition says a sub n plus 1 equals a sub n minus 1.5. So to get the next term in the sequence, we're going to take the term before it and subtract 1.5. Right, so this is that previous term. So 4 minus 1.5, that would be 2.5. Right, to visualize that out, I put 4 inside, minus 1.5, get 2.5. Then 2.5 goes in, and we're subtracting 1.5, so we get 1. Then subtract 1.5 again, negative 0.5. Subtract 1.5 again, negative 2. So our sequence is 4, 2.5, 1, negative 0.5, negative 2. So we can see that we can do it more efficiently as we start to recognize the components of the recursive definition. Same directions. Now a sub 0 equals negative 3, and a sub n equals 4 times a sub n minus 1 plus 10. Okay, so we've done 2 things here. First, they've given us a sub 0. So that means that n equals 0 to start. If I draw out the 5 blank spaces, and I put the n value underneath, they're telling me to start at n equals 0. And then 1, 2, 3, 4. So that could happen. we could start a sequence at n equals 0. It doesn't happen all that often, but it's something that we have to be aware of, that they could start at n equals 0 when they're defining the recursive definition. So now, look at how we're going to go from one term to the next. So the first term in the sequence is -3. So I'm going to put a box around a sub n minus 1. That's the previous term. So to get the next term in this sequence, I'm going to multiply the previous term by 4 and add 10. This is definitely more complex than some of the previous examples that we've looked at. So if I write underneath, so 4, -3 goes in the box, plus 10. So I'd have -12 plus 10, that's -2. And then -2 would go inside of the box plus 10. So -8 plus 10, that would be +2. Now let's try to find the last two terms without writing anything out. So 2 goes in, 4 times 2 is 8, plus 10, that's 18. And then 18 goes in, 18 times 4, so that's 40 and 32, so 72, plus 10, that's 82. So this sequence is -3, -2, 2, 18, 82. And they did two different things here. First, they started at a sub 0, which, as we know now, could happen. And they defined the next term with both multiplication and addition, so making our life a little bit more difficult. Our last example, a sub 1 equals 3, a sub n plus 1 equals a sub n plus n squared. Now, anytime I see n squared or an n term in the recursive definition, I know that it's going to be easiest to write out my blank spaces. 1, 2, 3, 4, 5. And underneath, I'm going to write the term number or the n value for each. N equals 1, 2, 3, 4, 5. I know to start at 1 in this example because a sub 1. They told me they're giving us the first term of the sequence. Okay, so first term is 3. So a sub n, that's the previous term that we boxed in all of the previous examples. But now we're adding n squared. So in this case, we're going to have to show our work for each one. So to find the second term, we're going to take 3, and we're going to add n squared. Well, for this term of the sequence, n equals 2. So we're adding 2 squared. So 3 plus 4, that's 7. Okay, so now 7 goes in the box plus n squared, but n is now 3, right? Underneath this blank space, n equals 3, so plus 3 squared. So 7 plus 9, 16. Keep going. Now 16 goes into our box plus n squared. Well, for this term, n equals 4, so plus 4 squared. So 16 plus 16 is 32. And then last one, 32 goes in the box. Now what's n? N equals 5. So n squared is 5 squared. So 32 plus 25, that's 57. So this sequence is 3, 7, 16, 32, 57. So that finishes off recursively defined sequences. But we covered a lot, starting with subscript notation. That's the notation we're going to use throughout the sequences unit. A recursively defined sequence gives us an initial term, and it relates terms of the sequence together. It gives us that pattern. Whether it's a sub n equals or a sub n plus 1 equals depends on really your choice or what the question is telling us. Recursive is really good for noticing the pattern of a sequence, really bad for finding the 100th term of a sequence. Imagine finding the 100th term of this sequence here. That was a lot of work just to get the first 5 terms, and we'd have to keep going all the way out to 100. So, at this point, practice with the recursively defined sequences before moving into our next video where we look at our first special type of sequence. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.